Okay, all right, so let's get started. So we were talking about this applications of the density matrix, and let's just recap it a little bit. So we did the density matrix last lecture, and basically what we're talking about here is how to do measurements, observables, operations with this. So basically the rule is that if you want to evolve a density matrix under a unitary, then you apply the unitary to both sides, left and right side of the density matrix. So this is because basically the density matrix consists of these this average of pure states, and it's a Ket-Bra type of construction, so you need to apply the U from both sides. Question, and for measurement observables, we need to, so the oh, yeah. Hi, Danny. So we just
Hi, Professor.
recap. Yeah. Hi.
Okay.
Yeah.
Congratulations on.
Oh yeah, thanks. Yeah. Yeah. So I'm at the hospital now, as I was telling Elin. Yeah, but it seems like it's still a while. So yeah, I'm just in the same floor, so they can always run in and get me at any time. So we'll see how it goes. Yeah, so just to continue the recap. So for observables, for pure states, we need to sandwich it with this the state, but for the density matrix, we take the trace with respect to the operator. So we have the operator A, that's the observable that we want to take the average with respect to, and then we have the density matrix. So this order can be either way. I've written it just like this. So it could be A row, but it could be row A. This is just the cyclic property of the trace. And yeah, so for maybe this is close to where we got up to last lecture, but if we want to talk about a mixed state that arises due to a measurement, then the state that you would get would look like this. And I think I explained this last lecture, but maybe it was a little bit confusing because I was also talking about the resulting state after a measurement here. And then now I'm also talking about measurement, but the difference here is that it's the average of all the different measurement outcomes. So previously this was one measurement outcome, and then the state that you get after you measure it for that particular case. So this is the jth outcome. Whereas this one is like you do this many times and then you average over all the different cases that you get. So so we can find the density matrix by basically looking at what the state is for each case and then multiplying by the probability of each of those measurement outcomes. So here we've got like, here's measurement outcome 1, where we start with the state psi, and here's measurement outcome 2 and 3, but then those occur with some probabilities. So in general, here's the states that we get on each particular measurement outcome, but then we need to average over with the associated probabilities. So if you put in this formula into here, then what you'll get is like a Pn on the numerator and 2 of these square root of p's in the denominator. So they exactly cancel out, right? So actually the expression that you get for the average state after a measurement is looks like this. So it's just mn times by the state, and then there's no probability. You don't need to put any probabilities in because yeah, they cancel out. So that's the case if you started with a pure state, like I've sort of illustrated here. But if you started with a mixed state, because you're also allowed to measure a mixed state too, the formula is very similar. It's just this one. So again, you just sandwich the density matrix by the measurement operators, and then you sum over all the different cases, and then that's the average state that you get. So that's basically where we got up to last time, and I think we did some example of that right at the end for a qubit. And yeah, so any questions on this slide or this or anything up to this point? No. Okay. Okay. All right. So then let's continue with sort of a related topic. So this time we're going to not view the, well, okay. So this time we're going to consider a different situation for getting this mixed state. So instead of starting, well, we're starting with the same thing. We're starting with some bunch of states that are coming in like this from our quantum particle source. And this time, instead of doing a measurement, we're going to actually, some kind of error is going to happen to it. And this is going to be some random process, right? And so there's a way to describe such error processes. And basically it looks exactly like measurement. And in fact, the modern kind of view of errors is that actually it's just the same as a measurement. It's just that you don't do it. Some uncontrolled source of noise that basically, you don't want usually does the measurement instead of you doing it. So actually a measurement really is no different really to some decoherence or some error process. It's just the only difference is that one is sort of human made and one is just sort of naturally occurring, or just sort of there without you wanting it to be there. So the way we basically write this is using so-called error operators. Well, I'm calling it error operators here. I think there might be various different names for it. Sometimes I think they're also called Krauss operators, but maybe for this course we just call it error operators. So the error operators act on the state, and just like with the measurement, this acts on the state. It creates some different version of the state, and there's various probabilities of this error occurring, and I'll give you examples of this later on. And so the average state that you get after this error process occurs is basically the same formula as for measurements, except that instead of M, I've got E, just simply because we've got errors occurring, not measurements. So yeah, and this error operator, which I'll give you a couple of examples of following now, has to follow some kind of mathematical properties. And so, for example, this after the error occurs, we should also get a density matrix. And because the density matrix has a trace of 1, whenever we act on this state rho with this error operator, the final state should also have a trace of 1. So this final rho dash should have a trace of 1 like this. But according to our definition from the previous page, if we just stick that in, then we can just manipulate this. So for example, here, I've again used this cyclic property of the trace where I can rearrange the order. So I put this operator before this one because for the trace we can interchange the ordering. And in order for this thing to be 1, then, well, it's easy to see from here, if we just think of this whole thing as some matrix, we need that thing to be the identity operator because, if it's not, then there's a possibility that this could be something other than 1. But if it's identity, then definitely this trace be 1 because initially this density matrix has a trace of 1. So this is actually one property that any error channel must satisfy, and it's called a trace preserving operation. It's pretty self-explanatory in a way because it's an operation that preserves the trace. The trace is the same as what it was before this error happened. Okay, so that's a little bit abstract. So let's just give a couple of examples of errors. So one quite common type of error is the so-called bit flip channel. So it's easy to understand. Basically what this is we start with some state here, and then what this error guy does is with some probability, which I'm going to call epsilon here, some probability epsilon, it will flip it, as in it will apply this X operation. Right? So this X operator is the operator that flips 0 to 1 and 1 to 0. Right? So it does that with probability epsilon, and otherwise it doesn't do anything. So the remaining time it just leaves this state as it is. So the way we write this, the error operators or the error channel. So this kind of operation is often called a channel. The reason why it's called a channel is because it's maybe the way that you sort of imagine it is that it's almost like it's like a pipe or something where you stick in a state on one side and then something happens inside the pipe and then the outside comes a different state. So it's like, well, a channel is normally something like a narrow river or something like that, but similar idea where you stick in something on one end and out comes something on the other side. So this whole process is called well, in this case, this is a particular error channel as in the terminology that people use. So in terms of the actual error operators, so for example, this would consist of just 2 error operators. And the first one is the one, according to the one that goes up here, this is the one where basically nothing happens to the state. So because nothing happens to it, it's proportional to the identity operator because the identity, does nothing to the state, right? The second one is proportional to X. And so that's because basically this is a bit flip channel, and it changes the, it flips the bits, right? 0 to 1, 1 to 0. And these square root factors, we need this because of this relation that I mentioned on the previous slide. So in order for this to be trace preserving, that means the state at the end has to have trace 1 if you started with the trace 1 at the beginning. Then we need it to satisfy this relation. And so basically like E dagger E dagger 0, E dagger, E dagger 0, E0 plus E dagger 1, E1, that's basically what that says, needs to be equal to identity, right? And so, yeah, so this term here is E dagger, I don't know, how do I draw on here? E, no, draw. I mean, I think you guys get it, but let me just try drawing. So this term here is the E dagger 0, E0 term, yeah, and this term here is the E dagger 1, E1 term, right? So spotlight, okay. So this square root factor is there such that when you add these two things here, and because x squared, this thing here is actually equal to identity. You can tell that because x is this 0, 1, 1, 1, 0, and then if you square this, it's actually equal to identity. So it will be equal to yeah, so it'll be equal to this one. So in order for these two to add to just regular identity with a coefficient of 1, then what we would need is actually this term here sort of to add with this one to give coefficient of 1, right? And so that's why this, and because there's two of these, and it's like E dagger E, because there's two of these, it needs to be square root in order for this to just give E epsilon and this factor to be 1 minus epsilon. Okay, so that's this bit flip channel. Any questions? Danny, did you have a question or? No, maybe not. Okay. Okay, and oh, all right. So how do I clear all drawings? Okay, here we go. So there's a very similar thing called the phase flip channel. So this is basically the same thing, except that you apply a Z operator to this. And just so that you can see why this is also an error. So let's, well, okay, so maybe typing is faster. So if psi is, say, equal to 0 plus like this, then basically what Z of psi does is to flip the sign of the 1 term like this. So when this error happens, it basically changes the sign between these two. And so this, of course, changing the sign is equally a kind of destructive error, if you like, as also a bit flip error. Kind of, because we're so used to thinking classically, we kind of think like the bit flip error, which is which would be this one, which bit flip error is kind of a little bit more serious than phase flip, because somehow you think, well, okay, changing 0 to 1 seems like a more serious error than just changing the phase. But actually, that's kind of incorrect, because that's only because we're so used to thinking classically and we're not used to thinking of superpositions. But this phase is equally as important in terms of the wave function as like the 0, 1 coefficients. So this is an equally sort of destructive error in a way, but it just acts in a totally different way. So the error, except that instead of x, it's actually z. So when the error occurs, we apply the z operator to this state, and otherwise nothing happens. It's identity. So in terms of the trace preserving nature, you can verify that just like before. You just this was the E dagger 0, E0 term, and this is the E dagger 1, E1 term. And if you substitute that into here, you can see that this is identity, so it preserves the trace. Okay, so that's phase flip. Okay, so let's do a little practice. So suppose the initial state is this one, the plus state, and we're going to apply this phase flip channel. So that's the second example, this guy, the one where we applied z, and acts with probability epsilon. So just using, well, the definition of this error channel. So work out what the resulting state is after if you start with this particular state. Okay, so I'll give you a couple of minutes to do that. Okay, how did you guys go? Did you get an answer?
Professor, do I need to first change this initial state to the density matrix?
Yes, yeah, you always need to change the initial state to the density matrix. So if the final state, basically you have to always evaluate with that. And here the initial state is rho. And so you need to change that to the density matrix, which will be
the outer product.
Product of, yeah, plus ket with bra plus, yeah, state. So I can reveal the answer. Okay, I will. Okay, whoops. So yeah, so the initial state is that. So you have the ket and the bra plus states, so it's like that. And kind of the easiest way really is to actually not necessarily work in with the matrices, because applying identity on the state is always the same. So essentially, this one will just give E0 rho, E0 dagger will give this same factor that we had on the previous slide, 1 minus E. Basically, the probability of the error not occurring. And then that's just the same state because no error has occurred. And then E1 rho, E1 dagger is basically, so we'll get 2 factors of the square root of epsilon. So that'll give the epsilon. Basically, that gives the probability factor of the error occurring. And then it's just the density matrix of the state with the error. So when the error occurs, so when Z acts on plus, then Z acting on plus gives minus, because, well, plus is 0 plus 1, and this is 0 state minus 1. So that's just equal to minus state, right? So that's the sort of the second case. So these are the 2 cases that we are talking about, like sort of here. So the first case is when nothing happens. Second case is when the Z error occurs. And then you've got that density matrix, you've got that density matrix, you add them together, and you can convert to the matrix form probably at the end here. That's maybe the easier kind of thing to do. And the density matrix for this one is the same as here. Density matrix for this one is like here, except that on the off-diagonal elements, it's got a minus here. So that would be the state for the minus density matrix for the minus state. And then if you combine those 2, then you will get, so on the diagonals, it's the same. So the diagonal elements are 1 minus E and E. So actually, there's no dependence on the epsilon on the diagonals. But because the off diagonal has an extra minus sign, so it's going to be on the off diagonal, it's going to be 1 minus epsilon in this spot here for the plus term, and then minus epsilon. So it's 1 minus epsilon, which is 1 minus 2 epsilon. So that's the state that you get. Hopefully you got that. And so actually, drawing, okay. So actually a nice way to kind of visualize this is on the block sphere again. So let's look at what this state, the thing that we just calculated, is in terms of the visualization on the block sphere. So just remember that when we did the calculation, well, for the pure states, basically the block sphere was defined as when you take the like expectation values of x, y, and z, and then you just plot it in this three-dimensional space, kind of pretending that x, y, z are like some kind of spatial coordinates. It's not. It's, you know, x, y, z are nothing got to do with spatial coordinates. There's some abstract quantum mechanical thing, but we can still well, try and plot it in that way, right? And so anyway, the block sphere is basically defined as with respect to these expectation values. And so we can take the expectation value of this state with respect to the x operators. And so, okay, so let me try and do, you know, so ordinarily I'd just do this on the whiteboard, right? But basically expectation value of that is defined as x times, in this case, rho prime. And so in this case, it's going to be something like 0, 1, top row. This is the first. Well, okay, maybe I'll put some spaces here so it's a bit easier to see. 1 minus 2 to epsilon. This is the second line. 1, 0, and 1 minus 2 epsilon 1. Okay, and then we need to take the trace of this whole thing, right? So we need to do that. So this is going to be trace of, okay, so when we do the matrix multiplication, this is going to be 1 minus 2e. The second row is going to be just 1. And the third row is going to be 1. And this one should be 1 minus 2e. Right. Yeah. Okay, and then we just take the trace of that. So sum of diagonals. Oh, I forgot a factor of a half here. So this had a factor of a half in front of for the density matrix. So maybe what I should do is divide by 2. Okay, divide by 2 here. So that basically means that it's going to be add both of these two, then divide by 2. So it's going to be 1 minus 2e. Right. So that's the expectation value with respect to x. Maybe I won't do the other, maybe I won't do y because it's going to be similar to that. So this is going to be like this. So this is going to be trace of, in this case, 1, 0. This is going to be the same, 1 minus 2e. 0 minus 1. 1 minus 2e, 1. Okay, and then I divide by 2. Running out of space. Trace of, and then we need to use matrix multiplication. This will be 1. This guy will be 1 minus 2e. This one will be, right, minus 1 plus 2e. And this one will be minus 1 divided by 2. And then if we take the trace of this matrix, it'll be 1 and minus 1, and so this is 0. Yeah. So basically, in this way, we can evaluate these kind of coordinates on the block sphere. And what you actually see here is that, well, it depends on this value epsilon, obviously, right? And remember, this epsilon was some kind of error probability, right? So this was like the probability of this error guy making this phase flip, right? So of course, if the error doesn't happen, so if epsilon is 0, then this x, this is at this position on the Bloch sphere, pointing in the x direction, and this is basically because no error happens, so it's exactly the same state. But when epsilon is a bit larger, then what will happen is that actually this position will gradually sort of go more towards the interior of the sphere. And actually, we never saw this for pure states. So for any pure state, that means any state that's of the form like, psi was equal to cosine of theta 0 plus e to the I phi sine of theta. So any state like this was always on the surface of the Bloch sphere. This is the first time we've seen any state that's actually in the middle. And and this is basically kind of a, sort of now an extension of this whole Bloch sphere idea that if you have a pure state, it's always on the surface. So this was a pure state. But if you have a mixed state, as in something including noise, then it starts to go into the interior of the sphere, and anything that's on the interior of the sphere is, you can think of it as having more noise than anything on the outside of the sphere. So it goes to the interior of the sphere. And so in fact, it sits along this line here, this red dashed line. And then what's interesting is that, and in fact, I think I didn't realize this until I made this slide, but actually, if epsilon is 1, then actually it goes all the way to the other side. So that actually the state would become the minus state, right? So why do you think that is? Like, why is it that it can go all the way to the other side? When epsilon is 1. So go back to this picture.
Oh, I think that when epsilon is 1 is pretty much like the measurement, where it's I mean that we are sure that we'll do the measurement and get a result as expected.
Actually, I think it's more like actually a like a unitary, because in a measurement, usually there will be always some several different cases, and I think you actually can't. You almost never have this situation where the measurement will do something deterministically, because when you have epsilon 1, then of course this happens with probability 1 and this happens with probability 0, right? So basically there's no like two cases, it's only one case that happens. And like usually in a measurement, there's always several cases that happen. So I think maybe the way to think about it is that in the case that it's like this Z, the Z operation happens like every single time. So it's really more like a gate. So in this case, this guy is more acting like a gate where you have an input state, and definitely this operation Z happens on it. And then here comes the output, and there's no randomness to it. So In this case, actually, maybe what I would say is that it's actually on the surface of the Bloch sphere, because it's actually again a pure state, because basically this guy just always turns this state into the version with the Z, and then so it turns plus into minus. In fact, if you started with minus, it turn it back into plus. So yeah, so I think it's basically, this is sort of a special case where it's this type of error is not really an error. It's actually turns into a gate. In fact, I didn't even notice this. I thought I read this chapter and I understood everything, and then I only noticed this when I made these slides. So I went, oh, okay, actually that's weird. Epsilon can be 1, and then it's actually you know, not a mixed state at all. So normally for these errors, you normally think of them as something that creates a mixed state from a pure state. So okay. Right. Yeah. So this is the picture that that the textbook Nielsen and Chuang has. So I just copied the same thing. But so here, what we just talked about there was like just an example where this plus state turns into something here. But more generally, of course, we can visualize what a general state, say you start with a pure state and then apply this dephasing channel. So this, sorry, I think my terminology isn't consistent. So I didn't mention on this slide here that this phase flip channel, another way to call this is the dephasing channel. Yeah, so maybe I could have just written the phase flip channel here as the title. If you start with any state on the Bloch sphere, basically what this does, so the example that we had was a state where it's starting here. And basically what this diagram means is that if it starts here, and I think these guys, yeah, took a value of epsilon 0.3. So it starts here on the surface, but then it goes somewhere more inside the sphere. So kind of this sphere, you can imagine it as being kind of sort of squashed and turns into this kind of oblong type of shape, right? So this is in general what happens. So if you started, for example, here, it would go like this way. If you start on the other side, then it would, whoops, it would go here. You can see that actually some points are invariant. So for example, if you start at the North Pole is still at the North Pole. And that makes sense because, so for example, in this calculation, if we change this to zero state, then if you apply the Z operator on 0, then Z on 0 actually does nothing, right? So Z acting on 0 is still 0. So because the thing that is supposed to cause the error, which is Z, actually doesn't affect that particular state. It's a special case. So in that case, it doesn't really matter. So that's why the state is actually invariant. So it doesn't change here. So this is the state 0, and then it's still there. For the state 1, well, it does kind of affect it, but actually only affects it up to like a global phase. So Z applied on 1 just pulls out this global phase, and then a global phase doesn't really do anything really to the state, as we've discussed before. So in that sense, also the South Pole also is invariant under this particular error. So it's really only states involving some superposition that will actually get affected. And the reason why it's called a dephasing channel, perhaps it's easiest to see this from maybe the previous slide. So I think I mentioned before that these off-diagonal terms are associated with the coherence. That means the superposition of the qubit. So remember, this state is starting here. Now imagine this case where epsilon is, say, like a half, right? In this case, this off-diagonal term would be equal to 0. And then this would turn into this state without any of these off-diagonal terms. And in that case, actually, it wouldn't matter whether we had like a plus phase or a minus phase, or maybe even over here where we have this state over here is like a 0 plus I1 state, and over here is 0 minus I1. So this thing here that we're talking about is kind of called a phase, right? So it's like here it's plus, here it's I, here it's -1, here it's minus I. Or we could have along this equator, it would be any complex e to the I phi phase. So basically what this phase flip channel does is kind of to wipe out this phase. So whatever you had your phase, you know, for this extreme case that epsilon is a half, it wouldn't matter what phase you had, it would just kind of totally wipe it out. That's why it's called the dephasing channel. Yeah, so you can also see it here. So anything on the around here basically kind of goes towards the middle, and then this phase is sort of, well, in this case it's just reduced, but in the extreme case it's totally removed. So another one is, so the first example that we did was the bit flip channel. So this is the case where we apply the X operator, and this is very similar to the Z, even though this diagram is a bit hard to understand, but this diagram kind of looks like it's getting squashed like a pancake. Actually, it's not true. It's also like an oblong shape, but it's just a bit hard to see. So in this case, the oblong is like, it's sort of along here. So in other words, basically this way is squashed, and also this way is squashed too. So it's squashed from above, and it's squashed sort of you know, diagonally, well, yeah, this way, right? So it's squashed that way, and it's also squashed that way, but it's not squashed that way. So this way, it's kept intact. It's a lot like this one where it was squashed this way, it was squashed this way, but it wasn't squashed this way. It was you know, kept intact along the z-axis. So you know, that kind of makes total sense, because the you know, the only difference between this bit flip channel was the fact that this is applying X, and here the phase flip channel applies Z. So you know, it should be basically the same thing up until some rotation, right? So of course we can think of something like a Y flip channel as well, where you know, something like Y is applied. Okay, so that's the bit flip channel. And yeah, so I mentioned this sort of extreme case of when epsilon was equal to a half for either the bit flip or the phase flip. Let me just remove this. So this state actually right in the middle of the block sphere is a bit of a special state, because the it's actually a kind of a completely random state. It's a state with the most sort of randomness in it. And of course we can understand this from, say, there's this error guy, he's producing either 0 or 1 with equal probability 50-50, then the density matrix of that would be equal to that. And this density matrix, you can verify that expectation value of x is equal to 0. Well, yeah, I guess it's obvious from, we already calculated this one. So what we're talking about now is a special case of epsilon equal to a half. So if epsilon is a half, then this term is 0, this term is 0, and you can see that this term is 0. So expectation value of x, y, z, they're all 0. But actually, it doesn't have to be just a mixture of 0 and 1. It could also be a mixture of plus and a half. And this actually produces also the same state. So actually, this is a bit of a interesting fact about the density matrix, that you think that the density matrix is somehow sort of, you know, unique in terms of its underlying states, right? So, you know, if you would sort of think that actually this state, which is a mixture of plus states and minus states, should actually be a different state to this state, which is a mixture of zeros and ones, because, you know, kind of they're physically different. But what the density matrix tells you is that actually, even though the underlying states are different, the density matrix is the same. And well, what I think that means is that essentially these two cases are physically different. That's true, but basically there's all kinds of, any kind of observables or anything that you do with it eventually gives the same results. So even though there's physically different underlying states, it sort of somehow gives the same result physically. So just sort of lumps all them kind of together. So, so in fact, yeah, different underlying states can give rise to the same density matrix. And this is one simple example. So even when this error devil guy produces pluses and minus, it also gives this. And in this case, the calculation looks a little bit different because, for example, here, this term here is actually the matrix plus 1, 1, you know, divided by 2. And then in this case, it's 1 minus 1 minus 1 divided by 2, right? So that's that state. So the first term is this state, second term is this state. And in this case, there's no zeros here because basically these guys cancel. So this 1 cancels with the minus 1, and then you end up with this thing. So actually any 50-50 mixture of orthogonal states, so not just plus minus or 0, 1, in fact, any 50-50 mixture will actually produce this state. And so this is actually a bit of a special property of this particular state because it comes from the fact that, you know, you could rotate this matrix, and because the density matrix is actually proportional to the identity, you can see that this is the identity matrix, right? Then this state actually is always equal to, still equal to I. So that's the case for a qubit, but for a more general, larger system, it would still be the same, I over d, and this would be also a completely mixed state for that system. Yeah. Okay. So, all right. Let's just do another quick question here. So we did the mix 50-50 mixture of 0, 1, and we got that state. We got a 50-50 mixture of plus and minus, we still got that state. So what I want you to just verify is that, say we got a 50-50 mixture of this one, these two states, let's call it theta and theta bar, just to check that that's still equal to this completely mixed state. So I'll just give you a couple of minutes to do that one. Okay, need more time or? Hmm. Right, okay, so you got that. Okay, great. Yep, so calculation goes like this. So basically just form the density matrix of each of the states, multiply it by the probabilities, half, half. So this is just outer product of this theta state. And so you get these cross terms on the off diagonals, cosine, sine, cosine, sine. And over here, this is the orthogonal state. So you can just verify that if you take the inner product between theta and theta bar, it will be equal to 0 because you have when you take the inner product of these two, you get cosine theta, sine theta, and over here minus sine theta, cosine theta. So these are orthogonal. So we take the outer product of that with itself. So here we get a minus sign here. These off diagonal terms cancel. And over here we get cosine squared plus sine squared, and here's sine squared and cosine squared, and so that's equal to 1. Yeah, so basically you can take any 50-50 mixture of orthogonal states, and actually it will always produce this completely mixed state. Okay, and so the last example that we're going to look at in terms of error channels is the depolarizing channel. So the way that this one works is that this error guy takes as an input this state rho, and with probability 1 minus epsilon does nothing, and with probability epsilon creates this completely mixed state, right? So this is like the state with the most amount of error in it, right? So we can write this channel like this. So it takes rho, turns it into epsilon I over 2. That's our completely mixed state. So we're doing qubit, by the way. Sorry, I forgot maybe to write this somewhere. It's qubit because it's the 2 here. And 1 minus epsilon times by rho. So it's pretty easy to calculate that, for example, expectation values of this state will be equal to something like this. And the reason why is because, so for example, if we did expectation value of x, so this is equal to trace of rho times x. And so here, after this error happens, then what the state is basically E times I of 2 plus 1 minus E rho. All that stuff times by x. And the trace is, you can just expand the sum in here. So it's going to be the same as I of 2 x plus trace of, well, in fact, we can already take this factor of E out here, because this is just a constant, and the constant always comes out of the trace. So, rho x. Then this is going to be E times trace of, and then identity matrix times x is always just x divided by 2 plus 1 minus E of, and this thing here, trace rho of x, is actually just the original expectation value. So I'm going to call that like x underscore 0. Maybe I'll just write, no, I'll write it like this. So that's the original value, whatever it was beforehand, right? Expectation value of that, whatever it was beforehand. And in terms of the trace of x, then because it's the matrix is something like this, 1, 0. So you can, I think, already see that the off-diagonal element, sum of off-diagonal elements is actually 0. So this term, first term, just totally drops out, and you just get this second term here that I wrote. In fact, the trace of actually all the Pauli operators are actually equal to 0. So whenever you just have the Pauli operator by itself, it's actually all 0. So that's why all these terms, the first term always drops out. The term corresponding to this one here always drops out, and you get that. And so finally, we can just visualize this thing in terms of the block sphere again. And the way that this one works is it's more symmetric. So if you look at this, it's easy to see that the final value of the block sphere is just the original value multiplied by some constant, and the constant is just usually, well, if epsilon is bigger than 1, bigger than 0, then it's going to be some factor less than 1, right? So this one will just sort of take your block sphere and then just make it smaller. So everything just goes towards the interior of the block sphere and just reduces the expectation value by some factor. And that's it. That's the end of all the lectures. So any questions on this slide set?
Professor, I have a question. Does it mean that if we apply a certain Pauli operator as an arrow or something, it just means squeeze the block sphere in some direction?
Yeah, right. So if we have any kind of error channel, so like these cases, right? Yeah. Yes, I think so. So yeah, so you can always have some error channel. You could have some error channel which is like not even X or Y or Z, some funny angle. And basically it's, you know, because there's always one direction where the state is unaffected by the error. Basically for the reasons I think I already said, that so any state, for example, in this Z case, there's always some unaffected states, right? And so there's basically the eigenstates of the Pauli operators are always unaffected, right? Because we suppose that this this devil guy is applying always some Z, then if it's an eigenstate, it's unaffected. And so here we're applying X, or, you know, any state that's an eigenstate will just be unaffected. So that's why it always sort of gets squished in one direction, because there's one axis which is sort of an eigenstate. But in this case, this completely well, this depolarizing channel, basically there's no state which is an eigenstate, because actually this one acts in a slightly different way. It's not that he applies some operator to the state, he just replaces the state with this I, completely mixed state. So there's basically no state that is unaffected. So that's why it sort of equally affects everything in all directions. So regardless, you know, there's no state that can escape the error in this case. Yeah, but for the for the case that you said, it was if you apply a Pauli operator, yeah, it's always tends to look like this. You know, it's kind of squished. Okay, any other questions? No? Okay, well, yeah, okay, if there's no questions, so it's right about on time. So, so yeah, so next lecture, I think I will be there. So I should be there, so on Thursday. And so, yeah, we'll just spend that lecture doing revision. So why don't you just like come up with a list of topics that you want to revise, and we'll just go through them.
Okay.
On Thursday. Okay. So, okay, so then see you on Thursday then.
Okay, see you on Thursday, Professor.
Yeah. Okay. Okay, great. Then, okay, I'll sign off.